Okay, so hello everyone. My name is TALA RUMMANI, and today my presentation to you will be about the potential for genetic engineering or genetic modification of human beings and its consequences. Since Watson and Crick's seminal work on the structure of DNA in 1953, the scientific community and society as a whole have wondered where the limits lie and whether the possibility of human versions of Dolly the sheep will come into being. I'd like you all to think of this scenario. It's the year 2031. Ash Lynx, of Japanese heritage, is born in Massachusetts in the USA. He's making headlines all over the world. The Miracle Boy is what newspapers are dubbing him. Why? Well, that's because Ash's father is unable to produce sperm due to a mutation on his Y chromosome, therefore rendering him infertile, at least in theory at the moment. But genetic tests confirm that Ash is indeed his son. How is that possible? To make Ash's conception possible, a fertility clinic took stem cells from his father. They corrected the Y chromosome mutation using CRISPR genome editing, and then derived sperm cells from the corrected cells. Those edited sperm cells were then used to fertilize his mother's eggs, cementing the change in all of his DNA. In other words, he is the first person in history whose genome has been edited, and he will not be the last. Well, most countries have outlawed genome editing after the news of his birth. Others have decided that it can have a limited use, mainly in helping couples who have trouble conceiving. Could this burgeoning field of science eventually provide a more cost-effective and patient-friendly process of conception compared to IVF? This is how the revolution is likely to begin. Soon there are hundreds of genome-edited children being born every year, then thousands. Those children are indistinguishable from their peers. That's actually because their genomes are entirely normal, so there is no difference. There is much talk about such editing of heritable DNA to prevent offspring from inheriting diseases such as cystic fibrosis. However, such diseases can already be prevented by screening IVF embryos before implantation. This begs the question, why would prospective parents decide to ditch pre-implantation genetic diagnosis in favor of the more costly and currently less established option of genome editing? Well, the answer to this is that PGD, pre-implantation genetic diagnosis, is only good for weeding out one or two harmful mutations at a time, whereas with genome editing, it should become possible to make dozens of changes at a time, making it a more cost-efficient process. Now, opponents of genetic engineering will call this a slippery slope. For proponents, it is sensible, even humanitarian. We all have hundreds of harmful mutations that increase our risk of diseases such as cancer, Alzheimer's, or mental health conditions. Therefore, proponents will say, why would we not eliminate those harmful mutations if we had the technology? In fact, once it can be done safely, it is arguably immoral not to. Why stop there? There are countless mutations that are deemed beneficial as well. For example, white Europeans are far less likely to develop diabetes compared to Africans and Asians. People in Scandinavia are renowned for their height, something that many cultures treat with great envy. Will parents try to have these more, aesthetic characteristics for their children? Where will the limits lie? Potentially, as soon as the 2030s, some countries may allow these variants to be introduced. Such interventions would be extremely controversial. Even more controversial would be adding gene variants that improve non-physical traits like personality, intelligence, or other traits that we highly value as a society. As yet, we don't know how to achieve that. We have yet to discover any single gene variants that make as significant a difference to IQ as environmental factors such as education, background, and wealth as well. In fact, the brain is so complex that we may never be able to predict what effect a specific mutation has on non-physical phenotypes. This means that introducing a brain-altering mutation that does not occur naturally would be a huge leap in the dark, something that many will find daunting, and even an ample reason for not going down this path. However, genome editing has the possibility to make individuals less prone to debilitating medical conditions, therefore lending credence to the argument that this is something science should pursue despite the current uncertainty. As time passes and the consequent acceptance of genome editing technology, it starts to become clear genome-edited children are healthier on average than those conceived the old-fashioned way. But this leads to these questions. Will this mean that parents who are wealthy will start to opt for genome editing, even if there is no need for them to do so? Will this allow the elite in society to widen the ever-increasing chasm between rich and poor? Will children born to these parents have yet another advantage conferred to them, simply via the size of their parents' bank accounts? Well, quite possibly, but this potential consequence is only speculation at the moment. As with all technological and societal shifts, the true consequences, both positive and negative, are almost impossible to predict so far in advance. I would like to end with an optimistic prediction. By the time genome editing is developed and cost-efficient enough, making it routine and less controversial, countries around the world will provide it to all their citizens who need it, irrespective of ability to pay, because the costs associated with genome editing are far, far outweighed by the savings in healthcare costs and the principle of having a happy and healthy population. Thank you everybody for listening to me, and I hope you have a great rest of your day.